Good afternoon and welcome to today's webinar, Understanding Machine Safety Functionality, presented by EHS Today, New Equipment Design and Machine Design. My name is Stephanie Valentick, Associate Editor for EHS Today, and in a moment I'll be turning things over to our speaker. I would like to thank Schmersal for sponsoring this afternoon's webcast. Before we begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during the session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the Help button below the slides. We welcome your questions during today's event. Just type your question into the question window on the left side of your screen and then hit the Submit button. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. Now let me introduce today's speaker. Mike DeRozier is a TUV certified functional safety engineer for machinery. His 20 years of experience include controls engineering to design, build, and integrate full machine control systems. His safety experience led him to help corporations to develop corporate safety standards, perform machine safeguarding risk assessments, machine safety training and design, as well as implementation of safety systems for all aspects of machinery, including electrical, electronic, pneumatic, hydraulic, and mechanical. Now let me turn things over to our presenter. Mike, the floor is yours.
All right, thanks, Stephanie. Well, good morning and good afternoon, everybody. Appreciate everybody joining us, those returning as well as those that are new to our webinars. Hopefully you find this webinar very informational and help you out with understanding safety when it comes to machine guarding. As we've done with past webinars, trying to break down some of the barriers of understanding machine safety and talking about different topics such as lockout, tagout versus machine guarding, or machine guarding characteristics, the process of machine guarding. We wanted to take this webinar and dive a little bit deeper in what we find that may be missing in the communication between when a risk analysis is done on the machine and the actual implementation that is done on the machine, and where are some of the gaps or shortcomings coming down to the machine safety functions themselves. A lot of you may already be aware of the standard ISO 13849 that has been put into place, that a lot of consensus standards and a lot of companies are now following. And one of the main things that they are defining is actual safety functions on a machine. What do those safety functions entail? These are just a couple of examples listed right out of Section 5 of the latest version of ISO 13849. And I'm going to say probably the top two that you see on most machines are the emergency stop functions. So your emergency stop push buttons or row pull switch to put the machine in an emergency stop condition, or the other one being the safety-rated stop function initiated by a safeguard. You have guard doors, light curtains, things of that nature that you're trying to put the machine into a safe state for operators to safely open up the door, do what they need to do for their production, their process, and come back out, close the door, and restart the machine again, but under a safe condition. What tends to happen a lot of times is you start the process by performing a risk analysis on the machine, identifying what the hazards are on the machine, and figuring out what level or quantitative approach those hazards meet or need to be remedied when it comes to a safety aspect. What type of guarding do you have to put on there? Is there gaps in the guarding? Is there gaps in the controls and the wiring of those controls? Once the risk analysis is done, you may look at a machine and say, okay, we have an emergency stop function, because we have multiple e-stops around the machine, and maybe we have a series of guard doors around the machine that has to initiate a safe stop of that machine. Great, that gets documented, gets put on a risk analysis report. Then a lot of times it may get turned over to somebody else to develop a solution to take care or remedy those hazards and implement it properly onto the piece of equipment. In doing that, we have to go through a decision tree of looking through the safety functions of a machine. Here's an example of the decision tree out of ISO 13849, looking at things such as severity of harm, frequency of exposure, possibility of avoiding it. Definitely, if you have questions on that, we can answer the questions. We have a separate webinar on ISO 13849. But ultimately, for this webinar, it's just getting down to a point of knowing what we need on the machine, but what do we have to look at downstream when it comes down to the solution, thus understanding machine safety functionality. So we're going to take an example of a safety-related stop function initiated by a safeguard. And for our example purposes, let's say our selection criteria, we know that the type of injury that can occur, maybe it's a crushing or an amputation of a finger, so we select S2 in this particular example. The frequency of exposure, maybe they're getting in there once every 5-10 minutes, so their frequency of exposure is high, and we're going to select an F2. The last criteria is selecting the possibility of avoidance. Let's say in this particular example, it is possible to avoid the hazard and avoid getting bit, so we select a P1. What that ultimately tells us is this particular safety function is required to be at performance level D per 13849 specifications. Please bear with me. Again, we're not going to go into details of the actual 13849 standard, but understanding the practical purposes of when we identify a function, what do we really need to do? So in this case, where we identified the function, we need to achieve a performance level D. We may decide to design a control category 3 architecture, which is a redundant monitored type of safety system. That's great. We put that on a risk analysis report. We identify the safety function. This safety function needs to meet a performance level D. So when I open up this guard door, I have to ensure that the system around opening up that guard door meets the performance level D, and as per the last slide, a control category 3 architecture. Statements made, that gap is recorded on the risk analysis report. That report gets turned over to somebody to take care of. All right, that's great. What do we do now? What has to happen? Part of it is the communication between the people that are actually doing the risk analysis and the people implementing it. What has to really be done on the machine to ensure a safe shutdown? So as you can see by the questions there, what is supposed to be taken down? Meaning, what are the hazards or what are the objects causing the hazard? Is it a moving hazard such as a crushing or a nipping point caused by a motor, a pneumatic or hydraulic cylinder? What is the real hazard by opening up that guard door per the risk analysis? Thus, what needs to be shut down? It might be that certain things are allowed to be maintain their energized state because they don't pose a particular hazard, such as maybe there's a vacuum generating, or to open up the door, by taking down the vacuum generator, there isn't a hazard if it's on or off, so you may determine that that's okay to be left energized. When you determine what does need to be taken down, do you know what safety levels those devices need to meet? Are you aware of safety approvals on those devices? Are you aware of how those connections are going to be taken down? Is it via the main power source? Is it inputs to that device controller, such as a servo drive or a robot controller? And then ultimately, how do you verify it? You put these things into place, and it may be a statement that says you must do it this way. How do you verify that it has been done and it has been done properly? So we want to go through some of those different aspects. So what do we actually have in a machine? There could be a lot of different things that causes hazards. You see a list of just some of them there. AC motors, DC motors, servos, steppers, fluid power, pneumatic cylinders, hydraulic cylinders. Is it hazard when they're extending, retracting? Both. Could be X-ray machines. You could have a vacuum that may or may not be hazardous. Thermal could be hot plates, heaters, flames, or chillers. Liquid nitrogen, liquid CO2, different things for refrigerants and freezing, which poses a hazard. Is it something that needs to be shut down or evacuated as a result of opening up that guard door? May or may not. You may need supplementary measures as well. But based off of that, what do you need to do to shut those different things down? Well, first, you need to identify what needs to be shut down. Which one of these action items, or I should say output devices, need to be taken down to ensure a safe condition when a person opens up that door to perform that particular task? So we're going to take an example here of a machine that has 4 output devices that causes hazards. Let's say there's pneumatic cylinders in there. There's a robot that's doing more of a pick and place into stations, an X-ray machine that performs some sort of test functionality, and maybe there's a servo lift. There's an elevator lift that's transporting product in and out of the machine. Operator works that machine, but now they have to go and open up that door. You go through your risk analysis saying, okay, we have that safety function of a guard door that's supposed to initiate a safe stop of that machine. What does that really mean? So based off of that pictogram there, as they state here, it's easy to state what the function needs to meet. But you really need to dig a little bit further to understand what is causing those hazards and the hazards associated with that particular function. How do you achieve the safe state? What is the result by opening up the door? What actually happens? What is the triggering? What output devices? So in this particular case, we need all 4 of those output devices shut down. But a lot of times where you see some of the gaps are, it may be inputs to a PLC, or it may be a device that nobody even thought to look to see if the device had safety approvals, and they just tapped into whatever the manufacturer's input block is to that particular device or controller. Do you really know if that meets the safety levels your risk analysis told you? If your risk analysis said we need performance level D category 3 architecture, how do we get there with the devices that we have? How are we achieving the safe state of the machine? So what happens a lot of times is when we look at identifying the safety function, in this case it's a guard door interlock function, we lay out what the actual triggering event is. Simply stated, as soon as I walk up to that guard door and I rotate the handle to pull that guard door open, the machine should enter in the safe state. So ultimately, what is the result? The result is machine enters safe state with no motion. So now we have our safety function identified, what the triggering event is, and what the result is. This is what ends up happening when you see a lot of risk analysis reports, that this is the data that's put in there. If you're going that far, this is the data that's being put in there, which, please don't get me wrong, it's great information to have and to know and understand and to put in your report and your documentation. But the problem being is just saying that the machine enters in a safe state without any motion, it's not enough information. What is that safe state? So you may need a little bit more details on whether it's your risk analysis report or your follow-up from that risk analysis report, somebody describing and defining what is the safe state of the machine. What is that actual result? So that may be increasing the details in that result field. In this particular example, we had those 4 different output devices, so we have to make sure that the robot controllers enters the guard interlock mode. The elevator lift that's being driven by a servo may need to be de-energized. We may need to dump the pneumatic air to enter the safe state. And we have to shut down the X-ray machine. There are 4 hazards on our machine associated with opening up the guard door. So in detailing out what is needed, this is what you really need to look at to understand truly what the function is of the machine, so you know how to properly implement a solution to ensure you're protecting people from serious harm. It's easy to go back to that pictogram and say, hey, the robot is really where the hazard is. We got to really focus in on the robot, but not think about the other output devices that can also be just as hazardous as the robot. It may not be as high of a hazard, where maybe the robot can amputate you, but one of the other things can certainly crush your fingers, for example, on the pneumatics as an example. Are we safely shutting those down per the safety level required based on our audit? So as we look at what that required architecture is, we stated performance level D, control category 3 was needed in this particular pictogram example. We now have to look at how do we ensure that we are truly shutting down all of our output devices. We got to look at each one of those. We got to pull manufacturer's documentation. How do we safely implement that into a machine? Once we know how to do it, we design it up, we wire it up, we have to validate it, either through design or by testing, and we'll talk a little bit about that in a few slides. So now we break down our result to those 4 key factors. What we really want to look at is each one individually. Again, we can look at a global aspect. Opening up the guard door, the machine has to enter a safe state. How are we accomplishing that? Here we have to look at the robot controller, the servo controls, the pneumatic controls, and the X-ray controls. How are we doing that on each one of those devices to meet the proper safety levels? So the first one we're going to look at is the robot controller. There's a big difference between older existing robot controllers and a lot of the new robot controllers that you can get commercially available now from several different robot manufacturers. With the updates and changes in the safeties with the various different robot standards from the ANSI RIA 1506 or the ISO or the CSA standards, they've gotten more aligned and they address safety in a lot more details and actually getting safety built into the robot controller. You can now get robots with the robot controller that has certain safety approvals already in it. and they give you the wiring instructions to safely implement a safety circuit where the robot is being integrated into. So in this example, where we have the robot in the center of the machine doing the pick and place, we have a guard door. Well, what's that guard door doing? That's tied to a proper safety controller for our Category 3, giving us the redundant outputs that we can feed into the robot controller. Meaning the robot controller now has certain safety approvals that you can tie to a redundant set of inputs that the manufacturer may identify as guard door interlock inputs. But what you find is in their documentation, they have specific wiring diagrams, and they make the claim that they have either self-certified or more often than not have had some sort of third party, being like TUV or BG, approve the controller safety functionality that guard door interlock may meet Control Category 3 Performance Level D or Control Category 4 Performance Level E, depending on the robot, the controller, and the construction. It's easy to make the statement, but do you have the documentation that really backs you up? How do you know you're wiring it up properly? Sometimes it's easy to think that you are, but until you have the manufacturer's installation instructions to support what you're doing, you need to make sure and look at those wiring diagrams and wire it per the manufacturer specifications, because that's what they have approved to meet that specific safety level for your machine. Make sure that wiring diagram per the manufacturer matches your schematics, but also with modern-day technology, there may be additional software or firmware in the robot controller that you may need to have set up as well, whether it be additional functions such as safe speed or setup or things of that nature. There may be certain parameters that need to be set up properly in addition to the wiring solution. It may not, but you need to make sure that with modern-day technology, you're looking at all facets of what the proper safety levels are to meet the approvals that the controller has received as a result. That's great on a new robot with a new robot controller that has those safety approvals, because it's easy to connect it. It's easy to make sure that the robot's in a safe state. The manufacturer is providing you the documentation to back up that implementation. What about an existing robot and robot controller that does not have any safety approvals? How do you handle that? It might be taking the power down on the robot. It may be the robot controller has separate power feeds for the motor drives and the input cards. It's not as clean or simple to properly integrate it, and because it's not simple, too many times what you see is an inhibit signal or an enabling input that gets interrupted to the robot, the controller, that when everything's working, it does what it's supposed to do. But when we're talking machine safeguarding, we're not concerned when things are working. We're concerned when faults occur and what happens. Because we don't want to get in the situation where we open up the door, we break in enabling input, but for some reason that enabling input does not work, and the robot all of a sudden takes off, and then ultimately creates a hazard and potentially somebody getting hurt as a result. Where a robot that has the safety approvals, it has the redundancies and checks inside the controller. When you have an existing controller that doesn't have that, you have to figure out how do you safely shut down that robot controller as a result. And there may be several different ways of doing it. It may be breaking the enabling signal and the motor power. There's not one catch-all solution that covers all of those, but the point of this webinar is you really need to take a look at what needs to be shut down and how you're truly accomplishing that safe shutdown of, in this case, the robot controller. If we look at the servo lifts, the elevator we discussed in the example, same thing. A lot of servo drives now come with safe torque off functionality as a standard feature built into the controller. Same thing with AC drives. We're seeing a lot of manufacturers have developed and released drives not as an option anymore, as a standard feature to achieve a safe torque off for that motor, so you don't have to have additional large power contactors to break down the three-phase power to the unit. But it's very similar to the robot controller. Do you have the documentation to support it and the wiring diagrams and the schematics to match it? And also with safety-related drives, there could be software parameters that enter that safe condition as well that you need to take in consideration. But like the robot controller, there's a lot of existing machines out there that may have servos or standard AC drives that do not have safety approvals that have that safe torque off. So what can you do? Unfortunately, a lot of times people are doing the same thing and breaking just the enabling signal because they don't want to remove the power to the drive. Unfortunately, that's not always the safe way of doing it, to ensure that that servo or that AC motor just doesn't randomly take off because a sensor got hit or a switch got bumped and all of a sudden motion takes place. You're not protecting people from being seriously hurt. So you may need to take down the three-phase power to the drive. Again, easy to say, not always easy to implement. You may have additional considerations to do that, where you may have to break the enable or the inhibit signal to the drive, where you can actually create a safer condition by using the dynamic braking function of the drive to get the motor to stop as quickly as possible, and then use a time delay to break that main power, because many drives do not like being seeing their power lost when the motor's in motion. Can get a freewheel condition, you can damage the drive. Definitely things that we don't want to have happen could happen in cases like that. So you really need to look at how do you safely accomplish shutting down an AC drive or a servo motor or a stepper motor. What's the safe means to meet the safety level the risk analysis comes up to requiring? The pneumatic dump. In a case like this, we may have seen in the machine that the safe condition is to remove the main air pressure coming into the machine. So maybe the machine's being fed with 80 psi. Putting a single dump valve on the machine, a lot of people tend to stop at the wire, they stop at the motor, and they use the standard single dump valves that they've always been using. Well, if the air is just as hazardous where it can cause an amputation hazard, we should be looking at a control category 3 solution for that. Several pneumatic manufacturers have come up with safety-rated 3-2 pneumatic dump valves as an example. They got safety approvals. They're control category 3, control category 4, performance level D or E approved, that you can use in a proper safety circuit. Are you not only wiring them up, are you piping them up properly? Some examples would be a manufacturer may supply the muffler built in so you don't restrict airflow, where other manufacturers may recommend a certain size muffler so you don't restrict airflow that you have to add on to the safety valve. When you restrict the flow, it means you could potentially trap pressure and a slower dissipation of air, where when somebody opens up that door, you may ultimately still pose a hazard because you're not safely dumping the air from the machine because of restriction of flow. You really need to pull the valve manufacturer's specifications. How do you properly wire it, as well as properly pipe it into your system to ensure a safe air dump? or it could be hydraulics if we're talking fluid power in general. The last one on this particular machine, we have, let's say, an X-ray machine that's doing an inspection on whatever parts being manipulated or put together or disassembled. They want to do an inspection to make sure the part meets proper quality standards as a final product. What do you do with the X-ray machine at that point in time? Because X-ray machines tend to have their own standards of safely handling the radioactive material that's embedded and sealed in the unit to develop the X-rays. But ultimately, you need to have protection via shutters. You can have an X-ray machine that has something called a shutter inhibit or a interlock inhibit that won't allow the X-ray to fire, or it could be not only an X-ray, but maybe it's a laser marking system or a ultrasonic welding system. A lot of those periphery controls may not have safety approvals that claims a certain control category to their controls. So how do you safely operate those machines and meet what your design intent is to based off of your risk analysis? Again, it could be very difficult because if the controllers don't have safety approvals, many times what you have to do is turn off the main power to that particular unit. Part of that might be putting shutters over the X-ray with proper lead protection that has its own set of safety switches on it that you have to make sure the shutters are closed and approved before you allow power to even go to that laser if you're not able to substantiate and back up via documentation that that X-ray controller or that laser marking controller meets a certain safety standard. The last step in the process is verifying and validating. So when we have our safety system, or I should say our safety function, we know what the guard door needs to do. We now know with our output devices what has to be shut down, and we figure out how that shutdown is supposed to occur and how we effectively and properly wire it up to meet our required safety performance level and control architecture. We really need to compare all those devices by looking at the manufacturer's installation instructions, comparing it to the schematics to make sure the schematics were drawn up per the manufacturer's installation instructions, or the designs have been implemented outside of the unit, such as breaking the main power per proper safety levels. But now part of what 13849 is calling out is not just checking it and saying it's wired properly. When you design, in this case, a control category 3 architecture, it's designed to handle a certain type of fault. So single fault, open circuit, short circuits on the safety switch. It could be cross shorts. If you're introducing the faults that could potentially occur, is the machine still safely shutting down and preventing you from restarting? Are all the output devices acting properly? So it's not just looking at faults occurring from the switch, it's faults occurred across the safety controller, or the outputs, the mechanically linked relays or mechanically linked contactors that are breaking the main power. What happens if one of those happens to fail? Does the output device, such as the robot controller, still enter its safe state and not restart because the controller detected the fault that it needed to detect? Easy to say. It's easy to say that this does this because that's what the manufacturer said it does. It's easy to put the blame on the manufacturer, but it still comes down to everybody knowing, understanding, and being able to test that it's doing what it needs to be doing. It's handling the safety devices, it's handling the safety circuit, it's handling the faults as they need to be handled for proper machine safety functionality. So as we look back at our pictogram again, we see that guard door with those 4 different hazards. As we go through each one of those, we can now see, okay, we looked at the robot controller. We used a robot that has a controller that has proper safety input circuits for a guard door interlock to lock that robot into position when a guard door is actuated. And we check that off of our list because we've checked the schematics. It's wired up properly. We now look at our elevator lift, and we say, okay, with the elevator, we have a servo drive that has the safe torque off. We set up the software parameters for that to do a dynamic braking to get it to stop as quickly as possible and provide a safe condition and not allowing that elevator lift to move when that door is opened. We looked at dumping the air. We put a proper 3-2 safety dump valve on our main 80 PSI that came into the machine. We made sure the proper mufflers, the feedback circuits or switches or devices that are mounted to that safety valve are fed back into our circuit to ensure that the implementation is done properly per manufacturer's installation instructions. And then our last part is going to be looking at the Xray. We looked at the Xray machine and we've determined that, hey, the Xray machine, as far as a control category 3, doesn't seem to meet the requirements for what we need to do to implement it in an overall machine. It may meet the requirements for the Xray standards, but we want to take it to a different level. So on top of its safety circuit, we're going to add the additional contactor or contactors to break the main power that's feeding that Xray if that guard door is ever open, to ensure that even if a failure in the existing safety circuit occurs, because we don't have any documentation to back up that that Xray controller meets any safety levels, we're putting that extra in there to make sure it meets a level that we accept as a control category 3, performance level D, to always ensure that's shut down so nobody's exposed at that particular time. Going through all that, I know what we really want to do is just cover that summary of what we need to look at. We identify the safety functions associated with the machine, which we seem to be doing more and more today when we do our risk analysis. But you really need to clearly define each function and how the safe condition needs to be achieved on the machine. If you're turning it over, whether it's somebody internal in your company in engineering or maintenance, or you're having a third-party integrator come in to modify your machine for you, or it's the original equipment manufacturer that's building a brand-new machine for you, you really need to understand how this machine is supposed to work, how it's supposed to be shut down, because how do you turn it over to anybody else if they don't know what you're looking for in the machine during the risk analysis process? You need to have that open line of communication and decide how that safe condition needs to be achieved upon actuating that safety function, whether it be an e-stop, a guard door, muting light curtain, a 3-position enabling circuit for setup mode. What is the safe state of the machine upon triggering of the safety device? How are you actually achieving it and backing it up? Which leads us into, you really have to make sure you have all the proper safety documentation from all the component manufacturers. Meaning any of your output devices, you have to have what their installation instructions are, especially nowadays where they do have safety functionality built into it, it's not just doing what you did in the past, it's doing it per their recommendations. Different drive manufacturers not only do it differently, but even within the same manufacturer, based off of the series of drive and the circuitry inside, there might be different ways of actually integrating safety in, which doesn't use the same nomenclature or labeling on the drive. You really need to have all the documentation for everything that you're doing related to that safety function. Once you have that, you have to compare that information to the schematics to make sure the schematics were drawn up properly per the manufacturer's installation instructions, and then verify that the machine is wired to the schematics. Mistakes can happen. You can get things running without having the safety wired up properly. Is the safety wired up properly? Because, again, we're not concerned when it's running. We're concerned when a fault occurs. Does the machine safely stop as it should and protect people from serious harm? And then validate it. Introduce your fault into the system and decide what needs to be done. It's easy to say this on a webinar. It's also easy to say that it's somebody else's responsibility. But at the end of the day, it's all of our responsibility to make sure we're all communicating, because if it's a EHS professional that's doing the risk analysis on the machine and they're writing up, okay, we've identified these safety functions, it's important for them to understand what the actual hazards, not only what the hazards are, what's creating the hazard, what's behind the scenes, meaning is it a servo motor, is it an X-ray machine, how are they being shut down? It's completely unfair to ask an EHS professional that doesn't have a controls background to evaluate schematics. You need to work concurrently with your controls engineers, your mechanical engineers. How are we achieving the safe state? Are we in agreement with this, that this is being done per the level of the risk analysis? The engineers need to help educate EHS on these are the things that are actually causing the hazards, because we can walk up to a machine, open up a door, and look and say, that's going to take my finger off. We need to do something about that, and then pass it on to somebody. But it has to be validated and verified what's really being done. Do we know what the output devices are that have to be put into their safe state to protect people from seriously being hurt? Okay? So at this point, given our timing, we'd like to open up the questions. Stephanie?
Thank you, Mike. A few of you have already submitted questions, so we're going to jump right in. If you would like to submit a question, there is a box on the left side of your screen that should allow you to enter some text, and you click on Submit, and that'll be sent right to us. All right. So for our first question, what happens if a manufacturer's guarding is deemed inadequate?
I can answer this a couple different ways, because I think the question is a little bit more general. If you're determined a manufacturer's guarding is inadequate, I think there could be a couple different answers based off of whether you're talking existing equipment, new equipment, how old the equipment is. It really depends, and I hope I'm answering this question properly for whoever asked this. If you're looking at existing equipment that you may have done your audit, the machine may have been made to safety standards. Maybe the machine's 20, 30 years old, and it was made to the safety standards at the time. Standards change. It's not like building a building where things are stationary and grandfathered in. There's no such thing as grandfather when it comes to machine safeguarding. Newer technologies, newer ways of doing things. That's why they always recommend you going back and keep performing risk analysis on machines to see if there's things that weren't feasible prior can now be feasible to increase the safety of the machine, protect people from getting hurt. If it's a new machine, then it might be a consideration of asking if that machine, or I should say the machine manufacturer, coordinating with him to say, this doesn't meet our safety standards for risk analysis. We need to have additional guarding. Now, whether that is cost on the OEM or cost on you as an end user, one of our webinars, one of the things that we tried to state is making sure that when you purchase a piece of equipment, that in the very front end, before you actually issue a purchase order, there's a clear, defined scope of expectations of machine guarding of what is required from a machine. There are machine builders out there that are extremely good at implementing proper safety measures. They see the value and they put that cost in there in the cost with their machine. There are some manufacturers out there that they feel that the safety is on the ownership of the end user and ultimate owner of the equipment. If you don't specify it in the front end, it may cost you in the back end. Make sure it's specified in the front. It could be into a gray area where you get into a little bit of debate between OEM and end user, where an OEM feels that their machine is safe based off of every guideline that they follow. They feel that they follow the guidelines per their interpretation, and that's really the key, interpretation. Unfortunately, a lot of standards are left up to interpretation, so what's your interpretation versus the OEM's interpretation? But it comes back to that communication communicated up front. It might be a machine that's only a year or 2 year old that you've accepted, but going through a risk analysis later, you may have found, based off of what we know now and what we learned, we should implement proper safety. Some people are worried about breaking warranties on machines. Talk to your OEMs about it. They may have a solution or they may have an idea to help you out with the machine safeguarding. I wish I can say that 100% of the time it's an automatic thing that proper safeguarding is put into place, but unfortunately, especially with competition coming and undercut costing of U.S. or European manufacturing, a lot of things that happens to reduce cost is safety is one of the first things that gets stripped out and put on the end user, and it ends up costing you more in the long run than getting that implemented up front. So forgive me if I didn't answer that per the question. If not, please just type in that question field again with more details.
Okay. The next question is, in the U.S., is there any regulation that requires equipment manufacturers to ensure that their equipment meets appropriate safety requirements, or is the due diligence only on the end user? And how does that end user know the equipment meets the safety requirements?
Oh, this could be a very loaded question and could be a whole other webinar in itself. Short answer, it's not easy. There's no OSHA regulations that puts onus, at least that I'm aware of, that puts the ownership on the equipment manufacturer. OSHA regulates the user of the equipment. So ultimately, in OSHA's eyes, if you're using the equipment, you need to make sure it's a safe piece of equipment. Does that make the OEM not responsible for safety whatsoever? In the United States, it's not so much OSHA, but lawsuits after the fact. If somebody were to get hurt, too many times anybody that had anything to do with that, the end user as well as the OEM, will get called into a lawsuit. And with a lot of the modern day standards, ISO standards, OSHA standards, ANSI standards, there's a lot of details when it comes to machine safeguarding. Even if it's not a specific one, it looks at the generic standards to say you knew of better principles and practices, you opted not to put it in there, and they can be pulled into that lawsuit as a result. So when it comes down to looking at what those regulations and who owns it, it ultimately comes down to both people own it. But coming back to the communication factor, you really need to clearly step that up and identify it on the very front end of things and work at it as a joint effort to make sure you're getting what needs to be a safe machine, and the OEM is designing that in the front end stages, which minimizes your cost impact.
Okay. What do you look for in a control safety certification?
I'm not exactly sure what they mean by control safety certification. I mean, there's companies out there like TUV that does certifications on specific equipment such as a robot controller, where the TUV may be looking at the design and they're looking at statistical data, probability of dangerous failures occurring, and what's happening inside that controller to deem a certification on a specific piece of a component. And that could be as simple as a guard door interlock switch, or to a servo drive or a robot controller that they've done their testing and introduced faults into the internal circuits, did it by design of component failures with resistors and capacitors and things of that nature that can cause dangerous failures, and how that controller particularly reacts as a result. When it comes to the overall implementation of the system, there's not very many people out there that will actually put a stamp on it and say, yep, your machine is particularly safe. And one of the reasons is liability in the U.S. Sometimes the language in the U.S. when it comes to liability gets a little crazy, and you say, you met toward compliance, but not actually say, I certified this piece of equipment to be safe, because ultimately things can happen after the fact that, manipulation and other aspects to it. So it could be a couple different things when it comes to control safety certification. Okay.
So who is responsible for the risk analysis? Is it the OEM or the final customer?
Ultimately, depending on the standard you read, it's typically both. The final customer should, with all of their existing equipment, should always going back and doing risk analysis on the machines. Just because they bought a machine and they expect the OEM to be an expert on everything related to that machine, that's not always the case. Just like the end user needs to learn machine safeguarding, so do some of the OEMs. They're very good. They could be certain topics or certain aspects or certain types of machines that they do really, really well with automation. Doesn't make them an expert on safety, especially if nobody's ever taught them what the proper way of doing it is. The other aspect is with a lot of the standards that are being written now, such as ISO 13849 and ISO 14119, they want the OEM to perform their own risk analysis on the machine to determine what needs to be done, how do they effectively guard it, and make sure that they're building a safe machine. And I hate to keep coming back to it, but it really does stem back to communication, that the OEM and the final customer are communicating of what those needs are. There are some customers that in their bid package, they require a copy of the risk analysis report that the OEM has done. Some OEMs do not agree to that. Some do. It really depends. Everybody has different feelings and opinions on that. So both should be responsible for risk analysis. But the final customer, even if you got a brand new machine, are you reviewing the risk analysis that was done? Is there things that you know of that you've implemented in your site that you want to see on that machine that should be specified? But just because a risk analysis was done on that new machine, you may look at it a year from now, 2 years, 3 years from now. You're going to redo that risk analysis and see, has anything happened since you got the machine? Maybe when you first got it, everything was great. It was packed up. It had all its proper guarding. Was anything changed on the machine? Maybe production changed and a different product, which means the guarding was changed to reflect the product, but something got missed in the modification of the guarding, where a risk analysis by the end customer would be able to capture that and make sure that was done properly when they modified the machine. So definitely both would have responsibility.
Okay. Is PL 13849 just an EU thing, or are you seeing other regions, such as North America, using it?
Oh, absolutely. Being an ISO standard, it's international, and a lot of the ISO standards do tend to stem from some sort of European norm, and it becomes implied, it becomes part of the CE machinery directive process of making sure you're complying with ISO 13849, because in Europe it ended up replacing EN 954-1 as the control standard. But as far as outside of Europe, it certainly has become a big thing. When you look at a lot of the ANSI standards, for example, ANSI is the American National Standards Institute. When you look at some of the most recent standards that have been modified or changed in the last 3 to 5 years, you will see that they reference ISO 13849. I can think of one right off the top of my head, like the printing press standards, the B65 standards, specifically call out performance levels for certain functions of the printing press. That's the minimum. Regardless of what you come up with, that's the minimum performance level. This function needs to meet performance level D. Even if your risk analysis says C, they want it to be D. And they're referring to performance levels, which is straight out of ISO 13849. And you'll see in the references in the back of the standard, ISO 13849-1 and 13849-2 are typically referenced in any new or updated standard. So the ISO standards are becoming more globally harmonized and being implemented into national standards now.
Okay, next question. How often do we need to test safety devices such as light curtains or laser beams?
With something like that, if it's a specific device, you need to look at manufacturers' recommendations to test that the device is functioning properly. For light curtains, since that was specific in the question, if you look at most manufacturers' installation instructions, they recommend a 6-month test most of the time to trip the light curtain beams all through the light curtain, as well as measure the stop time to make sure the safety distance is still mounted properly and nothing's changed in the machine that would impact the proper safety distance and proper safety functionality of that light curtain. But when you look at things like control category 3, category 4, or control reliability, part of what's happening in the overall safety system is they're being dynamically checked every time you actuate them. Other safety functions such as e-stops. E-stops you typically test more or should be testing more than the actual need. Hopefully you'll never need an e-stop. So there's nothing in any standard that I'm aware of that specifically states this, but a lot of times we may give a recommendation of testing e-stops once or twice a month to make sure that they're functioning properly. Even though they're a category 3, you're not dynamically testing them because you're not using them. They're there for emergency purposes. They're backups to the primary safety systems. So when it comes to an individual component, I would look at specifically manufacturers' installation instructions and what they say for recommended test procedures, where you can put in your PM schedule. And the overall safety system, it really depends on the safety level.
Okay, that concludes today's presentation. Any questions that we did not get to, we will be providing the mic so you can respond after this webinar. On behalf of EHS Today, New Equipment Digest, and Machine Design, I would like to thank Mike for his presentation. I would also like to thank Schmersal for making this webinar possible. And lastly, I would like to thank you, our audience, for your time and attention. We hope you found today's webinar valuable and will return for future webcasts. Have a great rest of the day.